Hi, and welcome to the podcast about graphing sinusoids. So this first part of this podcast is going to address the general equation for a sinusoid, which you see here in front of you. This is the general form of an equation for a sine function. There's no reason it has to be a sine. A sinusoid, remember, can be either sine or cosine. So I could do it exactly the same equation of this form, only with cosine instead of sine. It would still be a sinusoid, and everything I'm going to say here would apply to a cosine graph as well. Um, so what we're going to do is we're going to think about the role of the different translations and dilations that have been applied to the sine function for this graph. This is the most general sinusoid graph that we're going to be working with. One thing I want to start with before we actually talk about any of the transformations that actually have occurred here is that it's a little bit unclear from this general equation where the input is and where the output is. This whole section over here towards the right, this b minus times the quantity of theta minus d, there's some parentheses that we don't normally write. It's just kind of convention that we don't write them. But everything to the right of the sign in this form is part of the argument of sine. So b times the quantity theta minus d, that whole thing is the input into the sine function. And then once I evaluate sine, then I multiply the output by a and add c, right? So thinking back to what we know about transformations, we can say that a and c are outside transformations, which means they're going to affect the y coordinate, and b and d create inside transformations, which means that they're going to affect the x coordinate. Let's go ahead and kind of break these down piece by piece. What is the effect of c? Well, c is being, again, like I said, it's added on the outside of the input, right? So this is affecting the y coordinate. It's an outside transformation, and it's being added. So using what we remember about transformations, we can see that c is going to create a vertical translation by c units. This picture that I have here shows a sinusoid that has been translated upward a certain number of units. I want you to think for a second about knowing that the parent function of the sine graph looks the way that it does. I'm just trying one cycle here, but remember that the sinusoid goes on forever. What's a way that I can interpret c as quickly as possible? Well, I know that the center of the sine graph vertically is at y equals 0, right? So that's at y equals 0 right here. So if I've moved it up c units, right, that means that this number here is c, right? And this center line of the sinusoid happens at a value of y equals c, right? So I know that when I have a a vertical dilation like this, the center line of the sinusoid is going to be at y equals c, and then the graph is going to go up and down from there. We call this value of c, for this reason, we call it the sinusoidal axis. It's a pretty descriptive term because it's the axis of the sinusoid. The down the middle of the sinusoid is at y equals c. Okay, let's move on and let's look at this a value here. It's being multiplied by sine on the outside of the function. It's affecting y, and it's multiplied, so it's going to be a vertical dilation. Again, it's going to be a vertical dilation by a factor of a. What is that going to do if I have a sinusoid that only has a vertical dilation? What is that going to look like? Well, here's a graph that has a vertical dilation but nothing else going on. You can see what's happening, right, is the graph is getting taller and steeper, but it's not necessarily getting wider, right? It's not taking any more time to complete a cycle of the graph on the x-axis, but it is going up higher and down lower. And I also know that the height of my graph for a standard sinusoid that has been undilated is here at 1, right? So this is at y equals 1. So therefore, if I know that it is a times taller, that's telling me that the top of this graph is at y equals a. Now, one way of thinking about it is that, that's how far I go above the sinusoidal axis. Normally I go 1 above and 1 below the sinusoidal axis, but when I have a dilation, I'm going to go a above and a below the sinusoidal axis. This is called the amplitude. So far, so good. This is pretty straightforward. Just like with all functions, the inside transformations are a little bit trickier to understand. Instead of starting with b, we're going to actually start with d. D, we can see it's inside the argument of the function. It's being subtracted. That should lead us to believe that this is going to be a horizontal translation, and that's what it is. You may be a little bit thrown off by the fact that it has a the way the parentheses are in here, one way of thinking about it is what is going to make what value of d is going to make the argument be equal to 0. Or let me say that again, not what value of d, but what value of theta is going to make the argument be equal to 0. If I plug in a value of theta equals d, when I let theta equal d, that means the argument of sine is 0, right? So I'm taking sine of 0 degrees at theta equals d. So if I think about how that affects my graph here, right? Here, this point here corresponds to sine of 0 here, right? So this is 0 sine of 0, which in sine of 0 is 0, right? Now, if I think about on my translated graph what's going on, I'm saying that this point here is what makes the argument of sine equal to 0. That's d, right? So this is going to be d sine of 0, right? Because when I plug in the value of d, the argument of sine becomes 0. So if I think about what's really going on here, when I have minus d here inside the argument, what that's doing is it's shifting the graph d units to the right, which is the horizontal dilation, or excuse me, the horizontal translation of d units. A way of interpreting d is that it's kind of like the starting place of the graph, right? So what normally happens at d, or at theta equals 0 is going to happen at theta equals d. And the name for that is that d is called the phase displacement. Okay, so that is the role of d. Now we have one factor left, or one transformation left, and that's b, and it is the trickiest to understand. B does tell us the horizontal dilation, just like with all functions. When I multiply the inside of the argument, the argument of the function by some number b, that creates a horizontal dilation, not of b, but by a factor of 1 over b. In other words, if b is a number that's greater than 1, like 3 or 5 or 7, what it's going to do is make the graph 1/3 or 1/5 or 1/7 as y. Now, this is a little bit trickier than usual to interpret with a sinusoid, because when we talk about how wide a sinusoid is, that's particularly weird because a sinusoid has an infinite domain. It goes on forever. So we're really going to concentrate on the amount of time, or the change in x units to complete one cycle of a sinusoid. And we're going to define that quantity as called a period. So we have kind of a complicated graph here, but what I want you to do is focus on the black graph only for a second. If I look at the black graph, what I've drawn is one period, one cycle of the sinusoid y equals sine x, right? It's one cycle because it completes one full, it goes from the origin all the way up, back down, and then back up. So if I kept going on this graph to the right, I would be repeating itself, right? This is one full cycle. The period is the number of degrees it takes to complete that full cycle. Now, normally for sine, that's 360 degrees. If I look at, if I were to put a factor of b in there, what that's saying is that you're going to complete that full cycle in less than 360 degrees. I'll tell you right now that this graph that I've drawn on here has b equals 3. That makes it a little bit clearer, right? Because then you can kind of tell what's going on a little bit more readily. If you see here, the red graph completes 3 full cycles of sine in the time that it takes the black graph to complete one cycle, right? So the red graph goes up and down and back to the middle, up and down and back to the middle, up and down and back to the middle, 3 full cycles, and the time it takes the black graph to go up, down, and back to the middle just one time, right? So I've squished it by a factor of 3, and the period is 1/3 as big. So that is a summary of what all these different parts of the general sinusoid equation do. Next, in part 2 of this podcast, we're going to talk about what are some concrete steps that you can take in order to, when you have an equation, how do you get that equation and make a graph that has the appropriate scale and, goes through the right points.